Today, I will discuss about the sampling theorem and also the process of digital to analog conversion. Now, sampling theorem says that suppose a signal's highest frequency is FM. It can be either a low pass signal or a band pass signal. Then a proper sampling requires a sampling frequency of Fs, which has to be at least satisfying this condition. That means the maximum frequency component in the signal should be less than half the sampling frequency, or it can be said that the sampling frequency should be twice the maximum frequency component present in the signal. This number Fs by 2 is called the Nyquist frequency, and twice of maximum frequency component present in the signal is called the Nyquist rate. Now let's take an example. Consider an analog signal with frequencies between 0 and 3 kilohertz. That means the maximum frequency component present in the signal is 3 kilohertz. Therefore, a proper sampling requires at least 6 kilohertz of sampling frequency or higher. And if you do not choose a sampling frequency either 6 kilohertz or more than 6 kilohertz, then it can lead to aliasing. The effect of aliasing can be very disastrous. It can change the signal real frequency and even the signal real phase. We will talk about these aspects also in future lectures also in multi-rate signal processing. Let's look once again this process of, let's say this is a continuous time signal having this kind of shape. Then basically this is the sampled signal. How do you get the sampled signal? You just, mathematically speaking, you multiply the input signal with a train of impulses shifted by capital T. And then you will get the x delta t, which is your sampled signal. All right. So this is the mathematical explanation of how do you obtain the sampled signal from an analog signal. Okay. Now this slide actually shows the sampling in the frequency domain, meaning by, if you look at the analog spectrum, if you look at the spectrum of the analog signal, this omega minus capital omega minus pi by t or capital omega pi by t. Actually, pi by t in analog domain is corresponding to half the sampling frequency. Now, if this is the analog spectrum and you sample the signal and you obtain the digital spectrum will repeat. This small omega is the digital frequency, and this is the digital spectrum. Now, minus pi by capital T in analog spectrum is actually equivalent to minus pi in digital spectrum. Pi by capital T in analog spectrum is actually equal to pi in the digital spectrum. So actually the digital spectrum will vary from minus pi to pi, and further it will repeat with a period of 2 pi. All right. So this is the frequency response of an analog signal, and the below curve is the frequency response of the sampled analog signal. That's what I have already explained. As capital omega is pi by capital T corresponds to omega, which is the digital frequency, equal to pi, or f is equal to fs by 2. The digital spectrum is the same as the original analog spectrum, but repeats at multiples of the sampling frequency, fs. Fs is basically equal to 2 pi, right? So corresponding to 2 pi. After periods of 2 pi, the spectrum will repeat. Now, this is what this slide actually explains the aliasing process. When the analog spectrum is not band limited to minus pi by capital T to pi by capital T. That means it extends beyond minus pi by T on the negative side and beyond pi by T on the positive side. That's what is said here with this explanation. Then what will happen? The the Because the digital spectrum frequency response of the sampled analog signal and the digital spectrum, the spectra will repeat after a period of 2 pi, and it extends from. Now if you see here, the baseband frequencies, there will be aliasing. Let's see, if the sampling frequency fs is not sufficiently high, the spectrum centered on fs will fold over or alias into the baseband frequency. That means if this, let's say this is 2 pi and this is 0, the spectrum is centered at this frequency, and this spectrum will interfere into the baseband frequencies. The repetitive spectra will interfere into the base, and this frequency is actually the folding frequency. Folding frequency means where the aliasing will take place and the frequencies will fold over, and this point is also folding frequency, right, where the aliasing will take place. But this will happen only when the analog spectrum extends beyond minus pi by capital T uh, in the negative side and pi by capital T on the positive side. So the aliasing will take place. That's what is said here in this. If the signal is not, if the analog signal is not band limited, then the aliasing will take place in the signal. Now, after you convert the signal from analog to digital conversion, whether you will be able to recover the original signal from the digital at the receiver side, right? If you are able to, whether you will be able to receive the actual analog signal from the digital signal or not, that's the question. So that is actually done by a digital to analog converter, which we can call it as the signal recovery. The D2A conversion process is employed to convert the digital signal into an analog form after it has been digitally processed. After it has gone through the processing through the digital or DSP chip, whether the digital output of the DSP chip can be converted to an analog signal. So that's the question here. The reason for such conversion may be, for example, because ultimately you have to feed the signal to some device, whether it can be either a loudspeaker or to sound an alarm, and it will, these devices will take analog signal as the input. So you need to actually convert the digital signal into analog signal. The D2A process is shown in figure 9, which is on the next slide. I'm coming to that. So this is the digital signal processor. The output of the DSP chip will be y of n in digital form. It can be either 8 bits or 12 bits or 16 bits. This is the sampled version of the signal yn, and capital T is the sampling period. Now this signal, this digital signal will be applied to a D2A converter. Actually, the inputs to the D2A converter are series of impulses, while the output of the DAC has a staircase shape due to the as each impulse is held for a capital T seconds. Because of the holding action in the D2A converter, the output of the D2A converter will be a staircase shape. Now this staircase voltage will be passed through a low pass filter, which is basically acting as a reconstruction filter or smoothing filter to recover the original analog signal back. We will see how mathematically we can explain this whole process. The D2A converter shown in figure 9 is referred to as a zero order hold D2A zero order hold um, D2A converter. Now, by comparing its output y cap t and its input yn, it is evident that for each digital code fed into the D2A converter, its output is held for a time capital T. The result is the characteristic staircase shape of the D2A. I have already discussed it. The D2A output approximates the analog signal by a series of rectangular pulses whose height is equal to the corresponding value of the signal pulse. That's what these are. The height I am talking about is the height of this pulse. So these pulses will act from these pulses, which is basically the output of the D2A converter. After passing it through the reconstruction filter, I will be able to get the original analog signal back. Now, let's try to do the analysis and consider just one pulse out of these staircase shape of the output voltage of the D2A converter. Let's consider one pulse here, and this pulse will be defined as the impulse response of this pulse will be defined as um, 1 from 0 to t and 0 otherwise. All right, in the time domain. This is in the time domain. The pulse is in the expression is in the time domain for one pulse. Now, if we look at the corresponding frequency response in the continuous domain, because this I'm taking here the big omega, which is basically in the continuous domain only, and this is the formula, general formula of the frequency response of a signal, right? If you, because the pulse ranges from the value of the pulse is 1 from 0 to capital T, so that's why these limits are changed to 0 to capital T, and it is 1 in this range, so the expression reduces to the, if you solve this integral and do some manipulation by applying the Euler's formula, by taking this a of e to the power minus j big omega capital T by 2 out of the bracket, so you will be left with, you will be having this expression, which is basically equal to sine function, and this is the final output of the integral, right? This is, this expression is important, sine of big omega capital T by 2 divided by sine of big omega capital T by 2. This is basically a sinc function, right? Okay. Now, this is the frequency response. If we take the magnitude response of this expression, it will be only above the x-axis only, because we are taking the modulus here. Along the x-axis is big omega, that means the frequency, analog frequency. Along the y-axis is the magnitude response. And if we plot this magnitude response, we will be getting these type of pulses. Now, this sine of x by x is basically this big omega into capital T by 2 divided by this big omega capital T by 2. So x is basically big omega capital T by 2. So therefore, we get here sine x by x expression. All right. So this is the magnitude response of a rectangular pulse in the frequency domain. Now, in the frequency domain, the staircase action of the DAC introduces a type of distortion. Now, if you look at the, now this is the digital spectrum, which is basic. This is the digital spectrum in the discrete domain, because this small omega is the digital frequency, and this is the frequency response. We know that the frequency response is exactly same from minus pi to pi as the analog spectrum, but it will repeat with a period of 2 pi beyond minus pi to pi. And once, now this is the D2A output, which is basically a sine x function. as because the analysis that we are doing here is that we are taking one pulse, we are taking the frequency response of this pulse, and we find that the frequency response of this pulse is actually it's a sinc function. It is above the x-axis because we are taking the magnitude, so magnitude response. So therefore, this sin x by x is actually the magnitude response of the it is the D2A output. Now this sin x by x is actually because there are multiple pulses. If you see in this in the output of the uh, D2A converter, these are multiple pulses, and every pulse will lead to a sinc function type of waveform in the frequency. If we analyze the whole output of the DAC in frequency domain, so that actually introduces an error. We call that distortion as the sin x by x distortion or aperture distortion, where x, I have already explained, it is equal to big omega capital T by 2. All right. Now the amplitude of the output signal spectrum is multiplied by the sin x function, which acts like a low pass filter with high frequencies heavily attenuated. The sin x by x effect, actually this effect is due to the holding action, because that's why DAC gets a shape, or the DAC output gets a shape of the staircase voltage. And while we are doing the recovery, this will introduce an amplitude distortion. Now to mitigate the effect of, for a zero order hold from D2A holding action, the function sin by x sin x by x falls to about 4 dB at half the sampling frequency, giving an average error of about 36%. This is one example we can quote. And this is known as sin x by x type of distortion is known as the amplitude distortion or aperture error. Now this aperture error can be eliminated by equalization. In practice, this can be achieved by first passing the signal before converting it to analog through a digital filter whose amplitude frequency response has a x by sin x shape, so that it is just the reverse of this distortion. The response of the filter is x by sin x. The process of digital to analog conversion will introduce a sin x by x distortion, so the two are equalized. So that's the process of equalization to remove this aperture error. Now this is the aperture error, but it actually depends on what type of A to D converter you are looking for. I mean, that will depend on the specifications or the application for which the DAC is required. That means whether you actually require this compensation or not, that is the choice of the designer. But aperture error or amplitude distortion can be removed by having a pre-filter with a response of x by sin x. All right. Now, if you look at the block diagram of D2A converter, there is a low pass filter which we call as the reconstruction filter. Let's look at the reconstruction filter now. How the signal can be reconstructed. That means how the analog signal can be recovered from the digital input or to the DAC. Now the output of the D2A converter contains unwanted high frequency at multiples of the sampling frequency as well as the desired frequency component. That we have already seen because of the staircase voltage. Now the role of the output filter is to smooth out the steps in the D2A output, thereby removing the unwanted high frequency components. In general, the requirements of the anti-imaging filter are similar. So the reconstruction filter is actually known as anti-imaging filter. We will discuss this anti-imaging filter and anti-aliasing when we will discuss multi-rate signal processing in detail. But at present, this reconstruction filter is will be called as the anti-imaging filter. All right. So let's see how this filter can smoothen out the output voltage of the DAC. Now, if you look at the ideal D2A converter, the output should be impulses rather than that staircase voltage. Now, this is the ideal, this is the frequency response of the ideal low pass filter. Pulse, it is equal, it's a flat voltage from minus pi by capital T to pi by capital T. And this type of impulses are applied to the ideal low pass filter to recover the signal back. Now let's consider just one pulse, just one impulse, which is basically delta t function, and pass it through the low pass filter, right? And if you take the Fourier transform, you will get that this output will be, this is the Fourier transform in the Fourier domain, frequency domain, and this you once you take the inverse Fourier transform, you will get the signal back, and that signal will have a sinc function, sinc shape. So ht is sine pi t by capital T, right? So the output will be like this. This is actually the frequency response, right? It's not the time domain response, it's the frequency response. This is the time domain response. Now, if we apply the y caps t to the input of the filter, now y cap t and this ht is the impulse response of the filter. These will be convolved, and y cap t, we know that uh, y cap t is actually the convolution of the digital signal and the impulses. So these two will be convolved. All right. Now yn, this yn can be taken out of this expression, and this delta t minus n by capital T will be actually convolving with this sinc function. Now we know this property, then when the signal is multiplied by a shifted version of the pulses, time shifted pulses, you will get the signal, the shifted signal actually. So that's what the property we can apply here. Once you convolve the shifted impulses with the function, the function will itself get shifted. So that's what is done here. This sinc function gets shifted with gaps of capital T, and this will be yn sinc function, shifted versions of the sinc pulse. This response is for n equal to minus infinity to infinity. That means there will be now the original signal can be obtained by adding together an infinite number of sin x by x pulses, uh, because n varies from minus infinity to infinity. There will be infinite number of impulses, sin x by x pulses in the frequency domain. The nth sin x by x pulse is shifted through a distance uh, n capital T with respect to the origin and multiplied by a factor yn. That's what is actually given in this expression, that you will have multiple sin x by x pulses shifted by n capital T, and then the signal will be multiplied by this yn, right? Now this recovery process is actually called interpolation. We will see in the diagram that what this interpolation process is. Now this if you see the curve corresponding to y of 0, this impulse corresponds to this sinc function corresponds to y0, right? There will be multiples of sin x by x, as I said earlier, sinc functions. Now each discrete time sample is multiplied by a shifted sinc function. Summing these sinc functions will produce the original analog signal. Now if you interpolate, what is interpolation actually? You will get multiple sin x by x pulses or multiple sinc functions. Now you join the tip of these curves. You will actually interpolate the signal to this envelope is actually the original analog signal. And this process of reconstruction of the analog signal using the using the low pass filter, using the reconstruction filter, this process is known as interpolation. The signal xt is reconstructed from the samples by summation of weighted and shifted sin x by x pulse, right? So this is the process of digital to analog conversion using the reconstruction filter, and we also call this as a sinc filter or sinc function, reconstruction filter or smoothing filter. With this, I have explained the process of how an analog signal can be converted to a digital signal in my previous lecture. And in this lecture, I have covered with how you can recover the original analog signal back from the digital signal using a D2A converter and passing the output of the D2A converter through a low pass filter, which we call as the reconstruction filter. Thank you.